projectile motion going to be the topic of this lesson in my new general physics playlist. Now, if you find yourself struggling with this, you're in good company because this is a topic that a good chunk of students struggle with. But we're going to break it down. We're going to find out that it really is just kind of a synthesis of two one-dimensional problems combined into a single problem, and that we really can treat the x dimension and y dimension independently as was demonstrated in the last lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, so let's introduce projectile motion a little bit, and we're going to talk about it. This is our introduction to two-dimensional problems. Now, the first two problems we're going to do are going to be one-dimensional problems instead of two-dimensional problems, but they're going to set us up for the first actual 2D problem. So the idea is that the initial velocity is going to have oftentimes both x and y components, and we're going to treat those different components, those different dimensions, completely independent of one another. So if you take a look at what's going on in the x dimension, as long as we're ignoring air resistance, there's no drag on an object's motion in this case. And so it's going to have constant velocity. Well, if it's constant velocity, that means no acceleration, and we have just a single equation, therefore, to deal with that motion in the x dimension. But in the y dimension, there is gravity. And as long as you're near the surface of the Earth, that gravity has a constant magnitude of negative 9.8 meters per second squared. And that negative here again refers to the fact that it points downward. And that is constant. Everywhere along its journey, that acceleration has exactly that value as long as the entire time it's near the surface of the Earth, which is customary for us to deal with in this section. All right, so if we take a look at the motion here, there's a couple other things I want you to know. We're going to break up its initial velocity into components, an x component, a y component, same way we've learned to split vectors up into components and things of this sort. But big thing to note is that the x velocity is never going to change because there's nothing speeding up or slowing it down, again, in that horizontal dimension. But in the vertical dimension, that velocity is going to change because the acceleration due to gravity operates in the vertical direction pointing downward. And so on the way up, it's going to slow down the y component of the velocity all the way till it reaches that max height. When it reaches that max height, that y component of the velocity is going to be 0. So just like when you throw a marker straight up in the air, so at some point it's going to reach its max height and change directions. Well, all the way up, its velocity has been positive, but it's been getting slower and slower and slower. At the top, instantaneously, it has a velocity of 0 before it heads back down, and its velocity gets more and more negative all the way down, faster and faster and faster, in the negative direction. Cool, same thing works here. So it's still going to have an x component to its velocity up there. So its overall velocity is not necessarily 0 in this case, but the y component will go to 0 at that maximum height. So, and then all incidentally, oddly enough, gravity is going to have just as much time to operate it on the way back down. And so right at the end here, the final y velocity is going to be equal to whatever the original was, assuming it is hitting the ground at the same level from which it was launched. Now, this won't be true for all problems. You'll have some where it's going to be launched off a building and then hit the ground far lower. Well, then that won't be true. But as long as it's being launched and landing at exactly the same height, i.e. like ground level in this case, yeah, then that final y velocity will be equal to the initial y component of the velocity as well. Same thing as you throw it up in the air. So we saw as you throw it up in the air, as it comes back down, it'll have the same final velocity as the initial velocity on the way up, if it weren't for air resistance anyways. Okay. So let's deal with a couple of problems here. And again, you're going to look at this first one and be like, this is a two-dimensional projectile motion lesson, Chad. Yes, and we're going to start with a couple of one-dimensional problems first, though. So the first one is, we're going to have a hockey puck. And that hockey puck is going to be struck in the horizontal direction, sliding across the ice with a constant velocity of 86.6 meters per second. And I'll write that as an x component to its velocity, but in this case, it only has x velocity. And it's just going to slide across the ice here in this case with no friction. And the question is, well, how far does it travel in 10 seconds, 10.0 seconds? Okay, well, again, in this case, we have no acceleration. And so the only way we have calculated the displacement over the course of time is one equation. That's what we're going to use here. And specifically, instead of using delta r, we're going to use just the x component here. I realize, again, it's all x. But it's going to be x component of the velocity times time. And so in this case, that x component of the velocity is all the velocity. So 86.6 meters per second times 10.0 seconds. So, and I picked this example for a couple reasons. One, it's going to set us up for our first two-dimensional problem here in a little bit. And two, we can do the math in our head here, because multiplying by 10 is just moving the decimal over one place. And so our displacement here is 866 meters. Cool. In this case, 86.6 meters per second has 3 sig figs, 10.0 has 3 sig figs, so we want an answer in 3 sig figs, and it's 866. There's no rounding here. Using our exact numbers gives us exactly 866, which has 3 sig figs. So there we go. Cool. And again, this is just a one-dimensional problem with no acceleration, constant velocity, and we've been doing this for a whole chapter now. So, but again, this is going to be the basis for our first two-dimensional problem, which is not the next one, but the one after that. All right, so this next question is going to deal with a baseball being thrown perfectly vertically up in the air. Question says a baseball is thrown straight upward in the air with an initial velocity of 50.0 meters per second. Ignore air resistance. And then there's a two-part question. First is how long is the ball in the air? And the second is what is the ball's maximum height? So those are the two questions we want to answer here. So a couple things we should realize is if the ball's thrown perfectly vertical, it's going to go up and then come right back down. So a couple things we should realize. At the maximum trajectory here, its y velocity is going to be 0. In this case, its entire velocity is going to be 0 because there's only vertical motion here in this case. The other thing we should realize is that its final velocity, just as it's hitting the ground, is going to have the same magnitude as its initial velocity in the y direction on the way up. And so in this case, we might say that it's negative 50.0 meters per second if we cared. So, or just 50 meters per second pointed downwards. So just some things to realize right from the get-go. Okay, so from here, two parts of that question again. How long is the ball in the air? And then what is the maximum height? So for how long, so what you want to do is really split this in half in that vertical dimension and talk about the time up and the time down, because it's the same time. The time it takes to go from from 50 to 0 is going to be the same amount of time it takes to go from 0 to negative 50 as well. The change in velocity over the change in time equals acceleration. Well, the acceleration hasn't changed, and the change in velocity on the way up and the change in the velocity on the way down have the same magnitude, so the time's going to have to be the same as well. And we can kind of ballpark this. So notice gravity, acceleration due to gravity is negative 9.8 meters per second. And again, this is really approximately negative 10 meters per second. And I love being able to ballpark that in our head. It's really convenient. This came out really close to 10 because we can do a lot of ballparking in our head. So if you notice, if we start off with a velocity of 50 meters per second, well, the velocity initially points up, the acceleration points down. And when velocity and acceleration point in opposite directions, that's an object that's slowing down. And so if it starts at 50, well, then 1 second later, it's going to be slower by 9.8 meters per second. Well, again, I'm going to say that it's going to be roughly slower by about 10 meters per second. And so instead of 50 meters per second, after 1 second, it's going to be down to 40 meters per second. After 2 seconds, it's going to be down to 30 meters per second for a velocity. After 3 seconds, down to 20 meters per second for the y velocity. So how long does it take to get to 0? And you can see, oh, well, if it's 10 meters per second, that's going to take roughly 5 seconds. Now, technically, we're using this equation without realizing we're using an equation. If you have an intuitive feel for what acceleration is, and the numbers are nice, like they are here, when we ballpark gravity as negative 10 meters per second. So, but we're really just using this equation. The final velocity for the first half of the journey is 0. The initial velocity was 50 meters per second. Gravity, we were ballparking around 10. And if you realize, you still take a 0, take 0 minus the 50, you get negative 50, divided by the negative 10 gets you the 5 seconds. So we're using an equation, but if you don't have to use an equation because you have that intuitive understanding of what acceleration is, so much the better. But at the end of the day, if you want to use the equation, use the equation. So, and that's what we're going to do to actually solve this here. So we're going to again say v final in the y component equals v initial y component plus a times t. So we'll subtract this over. Again, that final for just the first half of the journey, 0 minus that 50 meters per second is equal to negative 10 meters per second times time. We'll divide through, we'll have negative 50 over negative 10, and we'll see that, yep, time would be 5 seconds. Well, again, let's get the exact answer. Let's put the exact 9.8 in there now, and let our calculator do some work for us. And we see that because we're going to be dividing by a little bit smaller number, we're going to get a little bit longer time. And so negative 50 divided by negative 9.8 is It's going to get us 5.102. So I guess in this case we want 3 sig figs, so 5.10 seconds. But keep in mind, that's just the way up. That's 5.10 seconds on the way up, which means on the way down, it's going to be an additional 5.10 seconds. And so the total time for the whole journey is actually going to be 10.2 seconds. All right, now that we got the total time, which is the first question, the second was, what is the ball's maximum height? Well, the maximum height is really just the displacement vertically on the way up. So from the height of 0 to the max height, that's the displacement going up. And it's equal in magnitude to the displacement on the way down, although on the way down that displacement would be negative, but in magnitude, same value. So you can just say, well, what's the displacement on the way up? Okay, great. How do we calculate displacement when we have uniform acceleration? Well, we've got 3 different ways. We've got this one, and this one that all have the displacement in there as long as we're just dealing with our y components. And again, my favorite is that first one. If I know I can calculate the average velocity because I know the initial and final, I go that way every time. So, and that's the case here. Our initial velocity again is 50 meters per second. Our final velocity for that first half of the journey is 0, which means the average of 50 and 0 is 25 meters per second. And the journey is roughly 5 seconds, 25 meters per second for 5 seconds. 25 times 5 would be roughly 125 meters. And again, we can ballpark this in our head and then do the actual calculation. And so in this case, delta y, dealing in the y dimension, equals the y component of the average velocity times time. Which again, the average velocity was 25 meters per second. First half of the journey is 5.10 seconds. We'll let our calculator do a little more work for us. We're going to get 127.55. So I'll make that 127.6 meters. And I carried 1 extra sig fig so I can see if I need to round this, because if you look at our input numbers, they're both 3 sig figs, 50.0 meters. So in this case, we're going to round this up to 128. Cool. And that is the displacement going up. Now, that's not the only way we could have done this. We could have used this equation as well, but we would have had a problem with this, at least in one sense. So if we would have tried to use that second equation, we would have said, well, the initial velocity is 50 meters per second. Plug it in there. The acceleration is negative 9.8 meters per second. And we'd have had time and time squared, and it would have been a quadratic, and that would have sucked. Definitely not the way to go. But you could have cheated a little bit and just said, well, but it's also equal to the displacement on the way down, at least in magnitude. And you could have figured out that way. And that's much easier because what's the initial velocity on the way down? Well, 0. And if the initial velocity on the way down is 0, you plug that in and that first term goes away, and all of a sudden you don't have a quadratic. You'll just be taking the square root instead. And you could have figured it out that way. Or you could have used this one as well. And again, whether it's the way up or the way down, you know the final velocity, you know the initial velocity, you know the acceleration, and you could have calculated the displacement there. Again, my preference is if I can use this first one, I almost always do. It's not always possible, or it's not always the most convenient, but if it is, if I have a way of knowing that average velocity because I know the initial and final, definitely the way I choose to go. So we're finally dealing with a two-dimensional problem now, and in this one we're going to have a baseball hit let's read it. A baseball is hit with an initial velocity of 100.0 meters per second at a launch angle of 30.0 degrees above the horizontal. Assume it is hit initially from ground level and that there is no air resistance. 3-part question. How long is the ball in the air? What is the maximum height reached by the ball? How far away from the batter does the ball land? So those are the questions we want to answer here. And so big thing we've got to realize that now, so our angle here is 30 degrees. So above the horizontal. Initial velocity again was 100 meters per second. And now we got x and y components. It's not perfectly horizontal, it's not perfectly vertical, it's somewhere in between. And so our x component here is going to be 100 meters per second times cosine of 30 degrees. So in cosine of 30 is 0.866, so you work this out. This is going to come out to 86.6 meters per second. So, and that should sound a little bit familiar because that was the x velocity we used back in the first one-dimensional problem we did just a little bit ago. Now, if we take a look at the y component of the velocity, so in this case, it's going to equal 100 meters per second times the sine of 30 degrees. And again, I like choosing 30 degrees because at least one of the parts of math is going to be easy. Sine of 30 is 1/2, exactly 1/2. And 1/2 of 100 is 50 meters per second, which was the initial velocity of the baseball we just threw up in the air in the last problem. And this is really a combination of the last two problems we've done. In the first problem with the hockey puck, we had an x velocity of 86.6 meters per second. Well, in the x dimension, there's no acceleration. Gravity only operates in the vertical dimension, not in the horizontal. And so it was constantly going to be 86.6 meters per second. And the only equation we had to work with to calculate displacement was this guy. That's not going to be any different now. Now, in the second problem we did, the very last one we just did, the initial y velocity, throwing the baseball up in the air, was 50 meters per second. And we figured out it was going to be 5.1 seconds on the way up and 5.2 seconds on the way back down. And that's not going to change here either. So the y, as far as the y part of it's concerned, it's exactly the same problem we just did. Now we've got to put the two problems together. So, but again, in the x dimension, there's no acceleration, only one equation. In the y dimension, we have gravity constantly acting downward, and we've got a suite of equations of how to deal with uniform acceleration. That's the deal. Now, where do you start with on one of these problems? You almost always are going to start with calculating how long. How long is the journey? But even if it's not the first question asked, it's usually the first one you need to answer. And the question you really need to answer is, which part of the motion, the x part of the motion or the y part of the motion, is the reason that the journey ends? Because this ball is going to get launched and it's going to land right there. Now, did it land because of what's going on in the x direction or because of what's going on in the y direction? Well, if it's landing on the ground, it's because of what's going on in the vertical dimension. So gravity's pulling it back down to hit the earth. And so then it's going to be the y set of, dealing with the y motion that's going to allow you to calculate for time. Now imagine for a minute that let's say this represents a building here. And there was a building sitting right here and the ball hits the building. Well, now all of a sudden it's hitting the building. So due to what's going on in the horizontal direction, and you'd actually have to use the horizontal dimensions motion to figure out the time in that case. And we'll do one of those examples in a little bit as well. But in this one, it's going to hit the ground, and we're going to use the y dimension motion to figure out the time. And that's where we'll start. All right, and so in this case, to figure out time, we've got a handful of equations there, but it's exactly the problem we just did a minute ago. And in this case, again, initial y velocity is 50 meters per second. Well, after 1 second, that would be down to roughly 40 meters per second, with gravity being roughly 10 meters per second per second. And in this case, on the way up, it's slowing down. On the way down, it's speeding it back up. So from 50 meters per second to down to roughly 40 meters per second, to 30 meters per second, to 20 meters per second, to 10 meters per second, and then finally at max height, reaching a y velocity of 0. That's going to take roughly 5 seconds on the way up, and then 5 more seconds on the way back down. Also, the initial y velocity is 50 meters per second. We should keep in mind that it's going to be it'll be exactly 50 meters per second right there as well, because we're ignoring air resistance. All right, so, but the math is exactly what we did a little bit ago, and we'll say that the final y velocity equals the initial y velocity plus at. So final y velocity for the first half of the journey is 0. So the initial y velocity, y component of the velocity, is 50 meters per second. The y acceleration is negative 9.8 meters per second, or meters per second squared, and then times time. We'll solve for time. It'll get negative 50 over negative 9.8. And we already know this is going to come out to 5.10 seconds. Cool, and that means that the total time for the way up and the way back down is just double that at 10.2 seconds. Again, exactly the same numbers from the last problem, which is why it's working out to be exactly the same amount of time. Okay, second question is, what is the max height? Well, it's exactly what it was in the last question as well. And we're going to use that time to get to the max height is 5.1 seconds. And we can use any one of these three equations. So in principle, to figure that out, these two have time, this one doesn't. But again, we also know the initial and final y components of the velocity and the y acceleration. We can calculate using that one as well. But again, my favorite is definitely that first one. Definitely my go-to in this case. So delta y is equal to the y component, the average velocity, times time. So, and the average y velocity again on the way up starts with an initial of 50 meters per second to 0. The average is going to be 25, therefore. Times that 5.1 seconds. This is probably still in my calculator, but I can't seem to pull it off the top of my head. 127, we rounded it to 128, right? 127.55 or 127.6. We rounded up to 128 meters for the max height. Total journey, 10.2 seconds. And then the question is, how far away does the ball land away from the batter? Horizontally. Sometimes we call that the range in projectile motion, that x displacement. And that's what we're solving for, x displacement. And again, with no acceleration in the x direction, constant velocity, the only equation we have is delta x equals the x component of the velocity times time. And again, it's that velocity that's constant with no acceleration in the x dimension. And plug and chug once again. X velocity was our 86.6 meters per second. It's not exactly 10 seconds here. In this case, it's 10.2 seconds. And so in this case, it will come out just slightly different than our original answer to the first problem we dealt with. But in principle, it's looking very similar here. So 86.6 times 10.2, and we're going to get 883.3, and I'll just round that down to 883 meters. Cool. Not so bad when we've already done the one-dimensional x problem, an analogous one-dimensional y problem, and then we just put them together. But again, one big key is, where do you start? Well, usually the first thing you're going to solve for is how long. And again, you got to decide, are you getting that from the x dimension or the y dimension? And again, figure out which dimension is causing the journey to end. And again, the ball was being pulled back down to the earth. That's due to gravity, which operates in the y dimension. Why we use the y dimension equations to first solve for time. All right, the next problem is going to be dealing with free fall. Sort of, but free fall now in two dimensions. So we're going to have both x and y components to deal with and stuff like this, but it's still going to be analogous to some of the free fall problems we did in the last chapter that were one-dimensional. So the question reads, a stone is thrown horizontally off a 100.0 meter tall building with an initial velocity of 25 meters per second. Ignore air resistance. Two-part question. How long does it take for the stone to reach the ground, and how far from the building does the stone hit the ground? Well, if we kind of follow that motion down here, so this thing's going to curve down and finally hit the earth. So, and again, we've got to deal with the x and y independently of each other, but one thing to note. So initially, this thing is thrown perfectly horizontally. So what that means is that the x component of the velocity is all of it, 25 meters per second, and the y component, it doesn't have one. So the initial y velocity is 0. And I really should say the initial x component is 0. I'm sorry, is 25 meters per second, but I don't have to say the initial. It's the velocity of the entire time. In the x dimension, there's no acceleration, and so the velocity is never going to change. It's going to be 25 meters per second horizontally throughout the entire motion, again, assuming we get to ignore air resistance as we're instructed to do. But the y velocity is going to be changing, but the initial y velocity is 0. Notice that it's no different than the case than if we dropped this stone off this 100-meter tall building. Its initial y velocity would be 0 as well. And in fact, if you followed the motion all the way down of a stone that's thrown horizontally and one that's dropped, you'd find that they would parallel each other and hit the ground at exactly the same time, because the y part of the velocity is all the same. Initial y velocity is 0 in both cases, the final would be the same in both cases, and the time to get there would be the same in both cases. The only difference is that one had an x velocity and one didn't, but the y parts of the motion were identical. All right, so let's see how this works. So again, two-part question. How long does it take for the stone to reach the ground, and how far from the building does the stone hit the ground? And again, in projectile motion, most of the time, what you're first going to be dealing with is time. And again, we got to talk about, well, why does this journey, why does this stone's journey come to an end? Because it hits the ground. Why does it hit the ground? Because of what's going on in the y dimension, because of gravity pulling it down, if you will. And so we're going to use that y dimension set of equations to figure out the time. And again, in the x dimension, this is all we've got to work with, constant velocity, no acceleration. In the y dimension, uniform acceleration due to gravity, and there's our suite of equations to work with. Which one do we want to use for time? Well, in this case, we have a problem. My go-to equation, my favorite, it's that first one. It's not going to work for us here. We know the initial y component of the velocity is 0. We don't know what the final y component of the velocity is. Could we figure it out? Yeah, we could, but it's going to be some work to figure it out just so that we could use this equation. Probably not the best choice in this case then. All right, what about the second one? Could we use that one instead to figure out the time? Well, the initial y velocity is 0. That's nice. So that first component will go away. And so technically we know that the y displacement, negative 100 meters down. We know the acceleration due to gravity, negative 9.8 meters per second. We could solve for the time right there as well. So that's going to be the way to go. And so in this case, in that y direction, delta y is going to equal the initial y component of velocity times time plus 1/2 the acceleration in the y direction, t squared. All right, and once again, the initial y component of the velocity is 0, so that first term goes away. And we're just left with, well, we'll start filling some numbers in. So, and we keep in mind that the displacement is downward, and I'm gonna write that as negative 100 meters. So if you get your signs wrong here and stuff like that, you're gonna have some problems. We'll see what I mean here in a second. So 1/2 acceleration due to gravity is negative 9.8 meters per second squared times t squared. If we would have forgot to make this negative but still made acceleration negative, we'd have found out we'd have been trying to take a square root of a negative number when we're all said and done, and that's a problem. So you got to remember that not only does acceleration point downward, but technically the displacement is in the downward direction for the motion here, and therefore that displacement is a negative number as well. So signs are kind of important much of the time here. All right, so if we take 100, and whether you want to divide by 1/2 or multiply by 2, and then divide by 9.8 or negative 9.8 as the case may be, we're going to get 20.4. Let's write out that step by step here. So t squared equals 20.4, let's put one more on there, 41. And that's in seconds squared. We'll take the square root of both sides. And we're going to get 4.52 seconds, which in this case is going to round to 4.5 seconds. Okay, first question is answered. Second question is, how far from the building does the stone hit the ground? And so now we want this displacement right here, which is the x displacement, delta x. Well, again, with no acceleration, constant velocity in the x direction, that's the only equation we have to work with. We need the x component of the velocity times time. X component of the velocity is constant throughout the entire journey of 25 meters per second. We've now figured out that the journey is going to last 4.5 seconds. And we can let our calculator go back to work for us. And we're going to get 112.5. In this case, if we look back at our input numbers, we're going to be limited by the 25 meters per second at 2 sig figs. And to round this to 2 sig figs, we'd round it down to 110 meters, expressed in the proper number of sig figs. Cool, that's the whole problem. So total time is 4.5 seconds. We use the y motion to figure that out because it's the y motion that's causing the journey to end. So, and then we figured out the x displacement, how far from the building it lands as well. All right, our last projectile motion question here. So in this case, we've got an arrow fired from a crossbow at a very tall building located 200 meters away with an initial velocity of 98 meters per second at an angle of 30 degrees above the horizontal. And the question is, at what height does the arrow strike the building? So this arrow is going to hit the building. Well, a couple things we don't know. We don't know if it's going to hit this building on the way up. We don't know if it's going to hit it on the way down. And the truth is, we don't even actually technically know, except for the way the problem's worded, if the arrow goes over the building. And in fact, the height of the building is not even given. It's just told that it's very tall. And in that case, it's worded in such a way that it's tall enough that the arrow is going to hit the building. It's not going to go over. Okay, the question is how far up? Well, and the truth is, whether we hit it on the way up still or after it hits max height and comes back down, it doesn't matter. all we need to figure out is what is the y displacement when this happens. And so whether we drew this out, that it hits it back on the way back down, doesn't matter. Because in that case, it doesn't matter as long as, or if we hit it on the way up or something like it, doesn't matter on the trajectory. The only thing we really have to worry about is what is the y displacement. And whether we're doing it for, on the way up or coming on back on the way down, the y displacement from here would be the same either way. We're going to label it exactly delta y in either case, and we'll calculate it exactly the same way as well. All right, so first thing I want to do is break that velocity up into x and y components. So your x component is going to be 98 meters per second times the cosine of 30 degrees. Your y component of your velocity is going to be 98 meters per second times the sine of 30 degrees. So, and again, I use sine of 30 because I like the math works, the way it works out. Sine of 30 is 1/2. Half of 98 is 49 meters per second for the y component of our velocity. So we'll see that's a very convenient number. And for the x component, 98 times the cosine of 30, it's going to get us 84.9. meters per second. Okay, we're going to start with time, and the question we have to ask ourselves is, again, why does this journey come to an end? So, well, it comes to an end because we hit the building. The question is, did we hit the building because of what happened in the x dimension or what happened in the y dimension? Well, again, in the previous problem, the journey of the stone came to an end, and the journey of the baseball in the problem before that came to an end because gravity pulled the ball into the ground. Is gravity pulling the ball into this building per se? So, well, gravity's not pulling anything in a horizontal dimension. So the reason this journey comes to the end is we're hitting the building based on the horizontal motion now, not the vertical. And that's why I chose this question. I wanted you to see an example of that. And so it is the x dimension that's going to deal with why in the world this journey is coming to an end. That's where we start to calculate the time. Well, again, in the x dimension, there's no acceleration. It's constant velocity. The only equation we have to work with is this guy. And so delta x equals v x t. So we'll solve for that time. The x displacement, we know that's going to be 200 meters. X velocity here is 84.9 meters per second. And then times time. And we can see, well, if we're traveling 84.9 meters per second horizontally to get a total displacement horizontally of 200 meters, it's going to take over 2 seconds. Well, how long exactly? 200 divided by 84.9 is going to be 2.36 seconds. Okay, so now we know how long the journey is. The question then is, well, then what would be the y displacement after 2.36 seconds has passed? Okay, well, this might be one way to go. Do we know the average y velocity? Well, we know the initial y velocity is 49 meters per second. At that point in the journey, do we know what the y velocity is? Well, no, we don't. So then we're not going to be able to calculate an average y velocity at this point. Okay, move on to the next equation. Could we use this one? Do we know the initial y velocity? Yes, it's 49. So do we know the time? Yes. Plug it in, 2.36 seconds. So do we know the acceleration due to gravity in the y direction? Yes, negative 9.8 meters per second squared. Yeah, we could use this one. We definitely could. So, and then we've got this one as well. So do we know the initial and final y velocities? We don't, so we can't use this one. The only one we can use is this one, at least very easily. All right, so we got delta y equals the initial y component times time plus 1/2 acceleration in the y direction times time squared. Initial y velocity was 49 meters per second. Time 2.36 seconds. Acceleration due to gravity, negative 9.8 meters per second, or meters per second squared. And again, times the time of 2.36 seconds. And we've got to remember not to forget to square that right there as well. And now we can let our calculator do the work. And again, we're actually not going to know if we're on the way up or if we're on the way down. And it doesn't matter. We'd solve for delta y the same way either way. All right, so 49 times 2.36 plus 1/2 times negative 9.8, really important to get your sign there, times 2.36 squared, and we're going to get 88.35 meters. And if we go back to our inputs here, it looks like the 98 meters per second here was given us 2 sig figs. That's going to be our limiter, actually. So when we round this, we're going to have to round it here, and it's going to round down, and so delta y is equal to 88 meters. That is your final answer. Now, this question doesn't deal with this, but my question for you is, did we hit this on the way up, or did we hit it on the way down as I diagrammed out? And how would we figure that out? Well, let's take a look at this for a second. So the initial y velocity is 49 meters per second, roughly 50 meters per second. And it's going to slow down on the way up 10 meters per second every second. How long is it going to take us to reach the max height? About 5 seconds. In fact, exactly 5 seconds in this problem. With it being 49 meters per second and gravity being 9.8 meters per second directed downward. Exactly 5 seconds. And so just to get to the max height would take 5 seconds. Well, we're way before that. And so I didn't diagram this correctly, and it didn't matter how we solved it. The truth is we're actually going to hit the building before we actually hit the maximum height in the trajectory of that arrow. Now, if you found this lesson helpful, give it a like. Happy studying.